Yes, so I hope the concept of symbol table is known to you now. Location, then lookup, that is searching for an entry, insertion, set attribute, get attribute, and these symbol tables are also called as keyed table because the entry in the symbol table will be done at position which will be calculated from the key. Okay, so key is important based on which the position will be calculated where that entry will be stored. Okay, and dictionary is also the similar data structure, but symbol table that is used for the any system program, whereas the dictionary it can be used by the user program or user application as well. So similar operations are done on the dictionary uh, data data structure also. Okay, these are all known as keyed tables where key and information pair is there. So in information you can have any structure like student structure or employee structure, anything. Okay, and we know that in searching we now want that searching complexity should be big of 1. Okay, that is what our need, but it will be very difficult to get this big of 1 complexity. uh, it is practically not possible. Even if we need that, we will try to check that it will give us big of 1 in most of the times. Okay, even if not big of 1, it should be as less as possible. Okay, these are the various data structures which can be used to represent the symbol table. Array, linked list, binary trees can be also used. And here we are going to learn in detail hash table. Okay, and OBST, AVL tree, RB tree, B tree, this will be studied in the next unit. So hash tables, we started with the hash table. Here we are going to use the concept of hashing. So hashing, what it does, it takes key as input and the hash function converts that key into the uh, possible position. Okay, position means the index in the array. So it calculates the index based on the key by applying certain functionality, which is called as hash function. Okay, so hash structure allows to retrieve the information directly. That means if a certain key, I want to insert a certain information with certain key, then I will apply hash function on it and I will calculate the uh, its possible position, and at that position I will directly access that position and insert the record at that position. Okay, so this is direct accessing of the memory. I'm accessing that particular position directly. That's why it is all called as direct access. Okay, so hashing, so in this case the insertion in the hash table will be done with big O of 1 because we are directly accessing that position and inserting. Okay, no need of accessing other records in that case. So hashing, it is key to address transformation. It is one of the searching scheme. Like we have linear search, binary search. Similarly, we can use hashing also for searching. Okay. So we have seen the example of this. If I want to store this a record with this employee ID, I have designed a hash function which is mod 100. Okay, so mod 100 will be applied on this particular key which will give me 45. So I will directly access info of 45 and insert the record of this particular employee ID at position 45. So this will be done with big O of 1. Similarly, if I apply hash function, the same hash function here, it will give me 14, position 14, which will be used for storing the information. Okay, like this hashing works. Here, elements are not stored according to value of the key. Okay, so value will not be considered. The hash value is considered in order to get the position. But elements are stored with respect to some function of the key, which is hash value. And searching technique we are using is called hashing technique. Efficiency of hash table lies with selection of hash function. So what type of hash function you are designing, that is important, so that it will take uh, execute in the faster way. And is are you able to recognize any problem with this hash function? Will always this address different for every key, or so that the position will be different? What is your expectation from this hash function? So why the message or no is there? Did you get my question? What is the issue with this hash function? Can you recognize it? Is there any issue associated with it? Will we always get big of 1 if we use a hash function and try to do insertion or searching? Will we get always big of 1 complexity? All the values with last 2 digits same will have same address, correct? So this is called as collision. This case, it will not give unique key, unique, not key, key should be unique, but address, we cannot say that every time it will give you the unique address. Okay, so yes, correct. So multiple keys can uh, take us to the same address. This is called as collision. Okay, this condition is called as collision. If multiple keys they are mapped to the same address by a hash function, then it is a collision case, and which can be resolved by applying certain collision resolution techniques. Okay, so we have to see that most of the collisions should not happen. Okay, that type of hash function, ideal hash function we are searching, where less number of collisions can happen. Okay, so we will try to see that. So efficiency of hash table lies with selection of hash function, and that hash function should give us less collision. Okay, that is the expectation. So example, see here example, this is the hash table, suppose, where I have to store the keys, and this -1 is saying that it is empty space. -1 is flag for empty space. Okay. So hash function key mod 100, this is our hash function suppose. Then if we want to insert these keys, this is at 4th location, this is at 0th location, this will get stored at location 1, location 2 and location 6. Okay, like this. Suppose we have this hash table. And if I want to search also, I will have to use same hash function. It is not like for insertion I am using another hash function and for searching I am using another. No. Same hash function you have to use while searching also. Okay, which you are using for insertion. The same will be used for searching as well. Okay, so if I want to search any key with the last 2 digits as 4, I will be first going to this position and check whether it is storing that key or not. Okay, so I have to apply the hash function at the time of searching as well, and I will search at that location directly. So hash function, the position of the key in the array is given by function called hash function. If suppose size of key is very large, that is 32-bit integer, then k is equal to 2 raised to 32. But actual number of items stored in the container are significantly less than mod k, then hash function is used. So here we have to do some prediction, and we have to occupy the memory to the that hash table bit larger so that it can occupy all the keys. Okay, all the different types of keys, but this is an ideal case. Every time we will not have that much of memory. Okay, So here we need the function like h is this is the different set of keys. This function maps the set of values to be stored in the container to subscript in array of length n. Okay, so this is our hash table index 0, 1, 2 till m minus 1. And in this hash table, we want to store the keys, various keys. This is called hash function. There may be many keys x and y such that x is not equal to y, but h of x is equal to h of y. Like you said, different keys can have same hash value. This situation is called as collision. Okay. So we have to learn different characteristics of hash function, which is the good hash function, and which are the various ways to calculate the hash value. Okay, how to design this hash function. So a good hash function, it should avoid collision, as I said, but it will be very difficult to avoid collision completely. In that case, you have to see that every key is having uh, every unique key will be mapped to unique address. In that case, it is possible. So if you use the relative array, we have seen absolute array and relative array. So if you are using absolute array, then it will be possible that for every key you have six different memory stored. But this is very ideal situation and which is not possible in real time. So we have to adjust the with the collisions. We have to resolve these collisions. A good hash function is easy and quick to compute. Okay, so it should not be very tough logic, because in real time you have to calculate multiple hash values. Okay, if I am logging to my bank website and if it is calculating the hash value of my password every time, then it is to be seen that it should be easy and quick. It should not take the delay. A good hash function tends to spread the keys evenly in the array. That means it should not happen that in the first part of the array, suppose first 10, 15 spaces, they are getting occupied with the keys, and the next part of the array is completely empty. This will not be the case in case of hash table. In hash table, we will see that it should be evenly spread. The keys should be occupied in every part of the array. So these are the different properties of good hash function. If it is spreading the keys properly throughout the array, if it is quick to compute, it is easy to understand, it should avoid the collision, then non-integer key should be converted to integer. So if my key is a string like name, then that name should also get converted into the integer, because it should get converted into the position in the array. Okay, so you have to apply the functionality like this. Equal keys must map to the same location. Okay, so it should not be like every time if I am giving the same key, it should not calculate different position, because see, if I calculate a position at the time of insertion, okay, suppose a particular key it is getting mapped to the position, then second time when I'm entering the same key during searching, it should get me to the same location, and so that I will access my record. Okay, so equal key must map to the same location. It should not give me different key. Otherwise, I will lose my record. So hash code map, it converts key to integer. So suppose, yes, if I have to enter two uh, keys, this is one is Arun and second is Runa. And if I'm using some functionality, then the functionality is just addition of ASCII values. Okay, so if I add the ASCII values of this string and ASCII values of this string as the letters are same, but arrangement is different. Still, in that case, I will get the same addition of ASCII values. Okay, and the same is the case with this also. Okay, if we add the ASCII values of this, because B is the next character of A and Q is the previous character of R. So if we add the ASCII values of this also, we will get the same string, same addition. Okay, so multiple keys they are getting mapped to the same address. So okay, this is one of the uh, functionality which I have chosen. Simply ASCII value addition, but multiple different keys can have the same addition. Okay, and we have to use the honors rule, which is polynomial accumulation, which is nothing but we have to check that the keys are spread evenly. That we will come back to this particular point afterwards. Okay, so in hash code map, the keys will be converted to integers, and in compression map, to find the location, that is index, like this, h of k is k mod m should be prime. This is one of the way. Okay, these are the two examples given. The k mod of m, this is very famous function type, hash function type, where if m is taken as prime, it is seen that we will get different locations every time, and the number of collisions will be less. Okay, how that we will discuss different examples of this. So different ways of doing the calculating the hash value. First is division, as we have seen. Simply division. The first order business of a hash function is to compute an integer value. If we expect the hash function to produce a valid index for our chosen table size, that integer will probably be out of range. Okay, so we have to map it to our range, whatever memory we have allocated. Suppose we have allocated memory of 15 elements. Then we have to do mod 15 for whatever calculation you have done. Suppose you have added ASCII characters, that is giving you certain value. You have to do mod 15 for that, so that that key will get accumulated in our table. Okay, that is easily remedied by modding the integer by the table size. There is some reason to believe that it is better if the table size is a prime. Okay, so by different studies, it is seen that if the table size is in prime, that is suppose 11, 13, 17, or at least has no small prime factors, okay, then the behavior of that table will be better. So this is simple technique, just modding with the size. Then second method is folding. Go through the example and check. Can you see what is this logic? Can you predict it? Yes. Can you predict what is this logic of hashing? So here, if this is my key, so 1, 2, 3 is kept as it is, but middle letters, this 4, 5, 6, they are written like 6, 5, 4, and then the addition will be done. Okay, instead of simple addition of 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this is boundary folding that you are dividing this key into three characters, three digits, and then you are adding it, and then some number is coming and you are doing mod for that. Okay. Or second thing is you're uh, doing the folding like this. This is reversing. 456 is converted into 654 and then the addition will be done. Okay. And this can be performed efficiently by doing bitwise operations, which you might have studied in ADE. The characters of the string can be XORed together, but small numbers uh, result. Chunks of characters can be XORed instead of uh, say integer size chunks. Okay, so you can use in between that XOR function, etc. So this will be completely your logic. Okay, this is shift folding and this is boundary folding. In shift folding, we are adding as it is, just dividing by in 3 digits, 3 digits, 3 digits. So if our key, suppose is this might be your employee ID, or this might be your bank account, certain characters from it. Okay, certain digits from your bank account number. Then if you are applying the logic that you are adding these three digits and then you are doing mod size, then that will give you the proper memory location. Similarly, you can do boundary folding after selecting these 9 characters. If you are taking first 3 digits as it is, next 3 digits you are reversing, and then next 3 digits as it is, and you are doing addition and then mod size. Okay, so this can give you certain location in your hash table. Is the folding clear? So you can have combination of these strategies in order to design your own hash function. Okay, which uh, so hash function always is used for security, and here the security lies. What function, hash function you are designing? Okay, that will be completely at your end. So no one else can predict, yes, you must have used this function, because multiple functions can be used to convert the key into address. So it is very difficult to predict such logic. And uh, suppose someone gets whatever you are calculating here, the addition of these digits, and then whatever mod you have done. That means the address is obtained to someone, and if they want to find out, or they have to trace what logic you have used in order to come to that location, it is very difficult from that. Okay, from address, if they want to have key, suppose they want to have your bank account number. Okay, but it will be very difficult to trace that in reverse, because multiple keys can have same address, can be mapped to the same address. Okay. Then second, next way or next function which can be used in hashing is mid square function, where square the key, then use the middle part as a result. Okay, so suppose this is the key, it is suppose square. Okay, and we are getting something like this. Out of this square value, we are selecting middle 3 digits as our, and then we are doing mod size of this. That can be, or if the hash table size is 1000, then we are using these 3 digits as it is to map as address in the hash table. Okay, are you getting it? Is it clear? And if you are using the bit uh, logic, okay, binary logic, then suppose this is the number which is represented as this. Okay, you can select some of the digits out of it, and then map convert it into a number and select the size. Okay, so these are the three various logics: division, that is mod, then folding, shift folding, boundary folding, or mid square function. Similarly, extraction. It is use only part of the key to compute the result. Okay, that is you can select first three digits or last four digits. Motivation may be related to distribution of the actual key values. For example, VT student IDs almost all begin with 904. So it would contribute no useful separation. Okay, so if in certain, suppose your GR number, most of the students will have the 219, 219, etc. So it will not add that much information into your hash value. So we can neglect that and select the remaining elements as part of the key. Okay, key calculation. So you can select some part of the unique information for calculation of key. Then radix transformation, where change the base of the representation of numeric key mod by table size. Not much of rational for it. The key is translated into another base. That is, if key is 345, change it to base 9, which is equal to 423 mod the table size. So we are doing the base change for this key, and then we are doing the mod. Okay, so you can use combination of this, or you can, these are few which are listed. Other than this, there are lot of logics, or you can have your own unique logic, so that will be the secured function. Okay, and you will come to know, you will only know what is the which are the different keys converted to what location. Okay, no one else can predict. Is the idea clear of hash function? Any doubt, anything that you would like to add before going ahead? Rohit, so there is no meaning of completely avoiding collision, because that is the very standard case, and we will have to see that for every key there should be memory available. Okay, that is, we have seen that absolute array. Okay, which is not possible. Okay, that's why it is not possible, or it is not ideal also, not real time to completely avoid the collision. We will come across collision. Okay, if we are having the property of hash function that same key should be mapped to same address. Okay, and it should not be reversely calculated, then, as we are not considering every element of the key in calculation of hash. Okay, that's why it will be not possible to avoid collision completely. And there is no, we are not having that expectation also, that we should completely avoid collision. Then we have to allocate a lot of memory. Okay, we have to balance all these things: memory utilization, fast calculation, proper searching, etc. And we know that we will come across the collisions. Okay, so we will see different ways of collision resolution. So collision, as we have seen, if we have the function like key mod 100. Okay, see, Rohit, if we have to allocate memory as it is, suppose for this key I'm going to use the same memory location, that is our absolute array, but it is no meaning that I will allocate all this memory. Okay, if I have only 1,000 keys to store, and if I'm allocating 40,000 memory spaces, then that is of no use. Okay, so if I want to store 1,000 keys, I will allocate only 1,000 memory. Okay, and if these are the two keys which I have to store in that 1,000 uh, memory, then this will be stored at 542, this will be stored at 942 location. Okay, If I am allocating only 100 spaces, suppose 100 employees are only there, okay, so I will map this to 42 and this will be also mapped to the same location 42. Then we have to think that how the collision will be resolved. That means one of them should leave that space, and that will get shifted to, that will find some another location, and it will get shifted to that location. Okay, so this is called as collision. So for avoiding collision, different methods are used. So basically, there are three different methods: open addressing, okay, open addressing, then separate chaining, that is using the linked list, combination of array and linked list. Separate chaining, it is one of the way, and bucket hashing. Okay. So open addressing is nothing but we will try to occupy the keys in the same memory space, same array. Okay, we will not use any extra memory than array. But here in separate chaining, we will be using extra memory. Okay, which is for that particular chain. We will see what is exactly separate chaining, the example of it. Okay, but these are the three uh, different methods under which this open addressing, we have some sub methods also which we have to learn in detail. Okay. First, direct hashing, which key itself is the same memory location. This is direct hashing. As we have seen, the absolute array, it is the same thing. That key itself is the memory location. So range of keys must be known in order to allocate the memory. Not possible for non-integer keys, and no possibility of collision in this case. But it is the ideal case and not practical. Okay, direct hashing always we cannot use. So basically, these are the two important methods: separate chaining and open addressing. Separate chaining in that array of linked list implementation. As we have designed the adjacency list in graph, the similar structure is there here for separate chaining. Okay, that means same key elements will be stored in the linked list of that particular key, that particular hash value. Okay. And in open addressing, we have linear probing, quadratic probing, double hashing, all these different sub methods. And open addressing is completely array based, whereas in separate chaining we have array of linked list. Okay, so this is separate chaining where, see, these are all the, this is universe of keys, the set, and out of that these are the actual keys which we are using in that universe of keys. These are the actual keys. Okay, k1, k2, k5, etc. And suppose these k1 and k4 they are having same hash value, then they will be there in the, this is the header for that hash value, and these will be the elements k1 and k4 stored in that particular chain or list. Similarly, this k5, k7, k2 they are mapping to the same hash value, so they will be linked together in the same chain or same list. Is it clear? So the hash table is implemented as array of linked list. Inserting an item R, suppose we have to insert one item R that hashes the index I, hashes at index I. So this is the hash value I of this element R. Then simply insertion into the linked list at position I. So we will go to the ith linked list and we will insert end or insert beginning in that particular list. Okay, synonyms are chained in the same list. So all these elements in that particular list they are called as synonyms because they will be having same hash value. Okay? So in order to search, suppose I have to search a particular record with key as k. So I will first find what is the hash value of k. I will go to that particular index and see, search in that list. That is synonyms. I will compare with those synonyms only. Okay, so what will be the searching complexity in this case, it is big of n. If all the n elements are having same hash value, then that will be big of n. Otherwise, whatever is the number of elements, maximum number of elements in the chain, that is our complexity. That means I have to compare only with the own chain elements. Okay, that is synonyms with same hash value elements. The comparison will be done with same hash value elements. Okay, so that will be the complexity. How hashing works in real life application, then we will also need to manage keys, so it will not direct us to same address like bank account id. Yes, Rohit, it will not take you to the same address. We will see with the examples. We have to discuss. Here we are learning only some concepts. Okay. After this, we will take real-time examples, real keys, and we will try to resolve the collision. Okay. You will come to know that properly, and we have to implement also this in our lab. Okay. So how we will reach to that particular position where our actual record is stored, that we will see. Okay, we have to do the comparison, but not with all. Here it is like linear search, but we are not linearly searching with all the keys. What we are doing, we are only comparing with our own hash value elements, that is synonyms. Okay, so the complexity is reduced, isn't it? The complexity is reduced. Then big O of n, we are only comparing with same hash value elements. Okay, xyz into key plus key mod key. XYZ is a number. Can we do these many operations together? Yes, there are many factors in designing such application. No, uh, if you are designing such hash function, no problem. But there are certain constraints. The time constraints are there. How much security you want? Is that particular application for which you are implementing security, is it that critical where you need such difficult function? Okay, so all these factors are there, and accordingly you have to decide that hash function. Okay, you can design your own hash function, no problem, but you have to see the memory requirements, time requirement, the calculation part of it. Okay, all those things, how many collisions are expected, all that analysis you have to do, and then you have to select a proper hash function. Okay, so in separate chaining, this is the example given. Suppose here the hash function is key mod 7. Okay, so whatever hash function we are using for insertion, same we have to use for retrieval also, that is searching. Retrieval of an item with hash address I is simply retrieval from the linked list at position I. So you have to only access that linked list with the required hash value, calculated hash value. Only that linked list will be accessed. Deletion of an item R with hash value I is simply deleting R from the linked list at position I. Okay, so you will access only one linked list or synonym linked list, and from that you will be deleting the required record. Example, load the keys. These are the different keys in this order in a hash table of size 7 using separate chaining with hash function h of key equal to key mod 7. So in this case, hash of 23 is 23 mod 7, which is 2. Okay, in the second list it will be inserted. So these are the hash values of all these key. These are the keys on which hash function is applied, and this is the hash value calculator. Okay, so if 0 is coming multiple times, that means it is collision, and they will be inserted, these values 21, 14, 7, they will be inserted here in the same chain. Okay, So synonyms are nothing but the values with same key. Okay, not same key, same hash value. H of 8 is 1, H of 15 is 1. So they are inserted in the list of 1. Okay, is separate chaining clear? So this structure, if you can see here, it is similar to our adjacency list structure. Any doubt in this separate chaining? So another example of separate chaining, suppose we have to insert these all keys. Okay, use the hash function hash to load the following commodity items into a hash table of size 13 using separate chaining. And here our hash function is like this. Okay, we are adding the ASCII values. All these ASCII values will be added, and mod 13 is done on it, on that addition, and that is giving us the hash value. So hash value of this is 1 7, and this orange is 12. Like that, hash value for every string is calculated. Okay, and these are the different records which we have to insert. Like this is the quantity, and this is the rate. Okay, this is the item. All these records we have to insert at the required position, and these will be the different hash values calculated on the string. Okay, so this is a separate chain structure which is created. Okay, so elements with same hash value will be in the same chain. This 1 1, these will be in the same chain, like that. Is it clear? Is this method clear? Any doubt in separate chaining? So alternative hash function for a string, we can have multiple hash functions. Okay, like Pratham just suggested. These can be the various functionalities which you can apply. Okay, C0, first character will be taken as it is, second will be multiplied with 27, third will be multiplied with 729, like that. You can have any functionality that you want. And then mod table size, so that the value will be mapped to required size. Okay, then again you can take the function like this. These are various functions. Okay, another type of function is like this: summation of all the characters, 26 into k plus whatever it is, character at kth position. Okay, so you can calculate your hash by using any of the function which you want. Instead of 729, you can use whatever value you want. You can use any value and design your own hash function. So that will be your secret function or secured function. So various advantages and disadvantages we will see of separate chaining. Advantages, first advantage is collision resolution is simple and efficient, because same uh, hash value elements, that is synonyms, they are stored in the same chain. So it is simple. The hash table can hold more elements without the large performance deterioration of open addressing. So here, out of our allocated array, we are using extra memory. Okay, those linked list elements, the memory will be dynamically allocated for the node, and we are inserting it in that list. So extra memory other than our hash table allocated memory, okay, we are using that. So load factor can be 1 or greater. So one means what? If load factor means whatever is the size of your hash table. This is the hash table actually. And if you are able to store more elements than this, so here we have allocated space for 13 elements only. Okay, but still we are able to store more than that number of elements because we are using listels. So this is load factor is more than 1. That is 100%. It is we are able to store more than 13 elements in this case. Okay. So load factor is 1 or greater. The performance of chaining declines much more slowly than open addressing. Okay, open addressing means we should not use any other extra memory than that array which we have allocated. Okay, that is open addressing. Deletion is easy. No special flag values are necessary. So we have to just go to that particular linked list and we have to delete it. Table size need not be a prime number here. Okay, that is not the case. The keys of the objects to be hashed need not be unique. So we can have multiple different keys stored in our hash table. And disadvantage is it requires implementation of a separate data structure for chains and code to manage it. So linked list, using linked list, it is somewhat not real time. Okay, it will be affecting the performance of our hashing. The main cost of chaining is extra space required for linked list. Okay, because in every node we have to store pointers. This will affect the memory also. For some languages, creating new nodes for linked list is expensive and slows down the system. Okay, so we should not, if we need faster access, faster hashing, then separate chaining is not the feasible method, and we have to move to open addressing. Okay, we will discuss open addressing in the